Hi guys, good afternoon in some places and good morning in others. I hope we're all doing well and I hope we're not nervous about the exams. I hope we are ready to get some information. All right, so far we have a couple people, Aidan, Megan, Jamelia, Hausen, Tyrone, Veronique, Duki, and Desmond. All right, so it's not one of our regular past paper marathons that we would do. It is more of a small crash course. So we're trying to go through natural systems. I'm not sure we will make it through all of it, but we will cover as much as we can. Um, Based on the votes on Instagram, most persons wanted to do physical geography first. So we will look at that. I wanted to show you what the syllabus looks like. If you have already seen the syllabus, just let me know. For the ones who have not seen the syllabus, let me know as well. So I just give you a small synopsis of what the syllabus looks like so that you know exactly what you're working with. All right? All right, good. So I see that a couple people have the syllabus. That's nice. Good morning, Elton. So we'll just look at the syllabus to see exactly how it works and how you can use it to your advantage. All right, so Destiny does not have the syllabus, but you can get a chance to look at it now, okay? So on your screen, you would have natural systems. That is basically, or physical geography. That section is physical geography. You have general objectives, then you would have the specific objectives. What you need to be paying attention to is your specific objectives. These basically tell you everything that CXC is asking you to cover on your exam, for your exam, within those 2 years. So your specific objectives, when my students are revising, I normally ask them to turn these specific objectives into questions. So all of these specific objectives that are listed out by CXC are actual questions that you can answer on your own. So if you are able to stay at home and answer all of these questions by yourself, that means you're good for the exam and you don't need to worry about anything at all. Okay? So students should be able to, and it gives you a list of things. So it has describe this, explain that, describe, explain, define, etc. So all of these, I figure when your teacher is teaching, they would have given you some objectives, or they would have written on the board what they plan to do for the session. So these are some of the things that you would see written down. Not only that, when you're doing an exam, these are some of the same questions that you would see for your exam. For example, define weathering, explain the process of weathering, explain the process of mass wasting or soil creep, etc. So all of these are things that are listed in the syllabus for your teacher to cover with you. Okay, so we are going to try to run through a bit. Um, I'll just skip over the specific objectives because there's another section that is called content. The section that is called content now, it gives you a deeper explanation of what CXC wants you to know. So it's a lot of stuff. So it is hard for you to just get a topic and know what on the topic you are required to know. So this is the content section for the physical part of geography. So they want you to know the internal structure of the Earth, including continental, oceanic plates, crust, mantle, and core. If you know that, you're fine. You would have covered that objective. They want you to know this as well: theory of plate tectonics, global distribution of plates, movement of plates, and the types of plate boundaries. So we're going to look at those a little. It would be good for you to just get out your textbook so we can just run through some of these just as a refresher. The occurrence and distribution of earthquake, island arc, volcanoes, fold mountains, major faults, and ocean trenches. So that would have been for the plate tectonic side of things for these three objectives here. Okay? If you're understanding what I'm saying, let me know. If you don't understand what's happening on the syllabus, let me know as well, so I can try to explain it a little clearer for you. Characteristics of intrusive and extrusive features. We have seen these on the multiple choice papers a lot of questions like these. Maybe they'll give you a diagram, maybe they'll give you actual questions that you need to pay attention to. So these are the specific intrusive features that they want you to look at, or they want you to know: sills, dikes, plugs, and batholiths. There's laccolith as well. We're not seeing them asking you to know that specifically. Extrusive features that CXC is asking you to know: caldera, shield volcano, composite volcano, and lava plateau. So I know that when you go in the textbook, there's a whole lot of information that you see. So when you're studying, it's best that you use the syllabus with your textbook. So you look for exactly what CXC is requiring of you, and then you look for that information in the textbook, so you don't spend the entire time reading through the entire book when it is not every single thing that is there that you're required to know. And then the next section would have been the rock cycle: igneous, sedimentary, and metamorphic. A lot of persons would have done this from what we call lower school, or grade 7 to 9, or form 1 to 3. So most teachers would not be covering it by the time you get to form 4 or form 5. But we can look at that as well. So we are going to just look at the top section first, just a small run through before we actually move on. All right. So the first one says internal structure of the Earth, including continental and oceanic plates, crust, mantle, and the core. The first thing you need to know regarding this section is the diagram of the Earth structure. So that diagram of the Earth structure, based on the past papers that we have seen, they don't go into a lot of detail and ask you a lot of questions about it. It's maybe 2 or 3 questions that we have come upon so far about the actual structure of the Earth. A lot of the detailed information on it is not necessarily asked. So things that you need to bear in mind are the 2 types of crust, which is continental crust and oceanic crust. You also need to know the specific layout, where the crust is, where the mantle is, where the core is. For CSEC, you are required to know inner core and outer core as well. You're required to know the makeup of the crust. So we know that continental crust, another word for that, remember, you're only doing multiple choice this time. So we don't need to go into a lot of detailed explanation about some of this stuff, since the multiple choice would require you to know the more specific things. For example, what is another name for the continental crust? That would have been Cl. And what does Cl stand for? It's really talking about the makeup, which is silica and aluminum. Another name for the oceanic crust is SEMA, which is also talking about the makeup, which is silica and magnesium. Oceanic crust is between 6 and 10 kilometers thick, and continental crust can be up to 70 kilometers thick. Regarding plate tectonics, the syllabus requires you to know the global distribution of the plates. In other words, they want you to know where the plates are, be able to name the plates, tell what type of plate it is, what kind of feature is associated with that plate. That would basically cover the second section. That's number 2 there. So theory of plate tectonics, including global distribution of plates, movement of the plates, and the type of plate boundaries, right? So global distribution of plate. If you are looking on the Caribbean map, you should be able to figure out where the Caribbean plate is. A very easy way for you to remember that is by looking for your specific island, because your island would have been on the Caribbean plate. So when you look for your island, you would see the Caribbean plate around that island, around those islands. Once you figure out the Caribbean plate, you know that above the Caribbean, you would have North America. So you would know where the North American plate is, and then you can figure out the other ones around it. So that's the easiest way for you to remember the actual plates, where they are and how they are distributed. So once you know that map, map that shows where the plates are situated, the next thing that you need to know is the movement of plates. We know that the plates have 3 types of movement. They move beside each other, parallel to each other. They move towards each other, and they move away from each other. So the plates that move towards each other, just like the word suggests, high echelon, just like the word suggests, those plates that move towards each other, they're called convergent plate margins. So the definition of the word converge means to come together. So convergent plate margin means that the plates are moving towards each other. When the plates are moving towards each other, think of 2 trucks driving towards each other on the road, right into each other. When they drive right into each other, obviously they're going to hit up, they're going to crash. And then things are going to happen, right? All sorts of different things are going to happen. So that would have been the plate movement for convergent first. We're going to go back to the things that would happen. For the divergent plate margin, just like the word suggests, to diverge means to move away or to go apart. So divergent, those 2 plates are moving away from each other. If you are moving away from each other, it means that you are creating space in between the 2 things. So those space that you're creating in between the 2 things, they would not lead to a collision, it would create other things. Okay? And then the third movement would have been parallel to each other. If you're parallel, you're moving beside each other. The thing with this plate margin is that they actually touch from time to time. And it is these small touches or glitches or hitching on each other that would give us the earthquakes. So those are the 3 plate movements. For the convergent plate margin, because they're coming together, they're converging. Another name for that is destructive plate margin, because things are going to get destroyed. For the divergent plate margin, because they're moving away and then you have new material that is coming up, new land being formed, that one is called your constructive plate margin, because things are being constructed. So those are our 3 plate movements. For the parallel, or otherwise called passive, or the transform plate margin, they are just moving past each other. So it is passive because a lot of things are not happening. We can look at it in that way. They're not colliding. They're not creating new land. So we call it passive or transform plate boundary. So those are the movement of the plates. and the type of plate boundaries that they create. What we see sometimes on the exam as well are diagrams which show you the movement that is happening, and you are asked what feature is expected to be formed at that area, or they show you the feature that is formed, and then they ask you what type of plate margin it is that is there. Those are the types of multiple choice questions that we have seen already relating to this specific objective. So for objective number 3, occurrence and distribution of earthquakes, island arcs, volcanoes, fold mountains, major faults, and ocean trenches. So occurrence is basically asking you where is it that they happen. Distribution is asking you how they are spread out across the world. That's what occurrence and distribution is talking about. So to know the occurrence and distribution, you just need to know where each plate is, what is happening at each plate, what kind of movement is happening. For example, we know that all 3 plates give us earthquakes because the earthquake is as a result of the movement, and all 3 plate types, are moving. As a result of that, all of them will give us earthquakes. So we can look at this and say, relating to occurrence and distribution of earthquakes, the earthquake is going to be at every single plate boundary. It can happen at every single plate boundary, simply because all 3 plate margins will give us an earthquake. In terms of island arcs would have been basically a line of volcanic islands. This line of volcanic islands is most likely found along a convergent plate boundary. So when the plates converge, what we normally see in a textbook is really just a cross section of it. So just what it would look like from if we were to cut the earth in pieces, then if we were to cut it in two, what it would look like from that end. But the plate is a big thing, so it would stretch all the way across. So it means all of the one plate would be going towards the other plate. So when the subducting is supposed to happen, all of that one plate is subducting. So along that boundary where the subducting is taking place, it means there is a potential for volcanoes to be formed all along the boundary. So that is how you would end up with that island arc, where you have a line of islands or you have a line of volcanoes as a result of the plate boundary that is there. So if you are asked about an island arc, it would have more than likely been at a convergent plate boundary. For the volcanoes, the volcano is formed when, well, to put it simply, once you have magma that is escaping the Earth's surface, the Earth's crust, and it is coming on to the Earth's surface, where it is going to be now called lava, then you would have a volcano. Based on the 3 types of plate boundaries, you would have volcanic activity at convergent and at divergent plate boundaries. The divergent and the convergent plate boundaries, they would produce different types of volcanoes generally. So at a convergent plate boundary, you are more than likely to see more destructive earthquakes, more destructive volcanoes, more violent volcanoes. So these would have a stronger silica content. These would have magma that is acidic. Acidic lava is thick. It cools quickly, and it is very explosive. When we have the acidic lava that is coming up onto the Earth's surface, the fact that it cools quickly, it means that the type of volcanoes that would have been created. I'm gone into number 4. Sorry about that. We'll get back to the specific description of the volcanoes when we get to number 4 here. We're still here. We're just talking about the distribution of volcanoes. So in the distribution of volcanoes, it is basically wherever you have convergent plates boundaries and wherever you have divergent plate boundaries. You would not have the volcanoes where you have just a transform plate boundary. For the fold mountains, that would have been where you have the convergent plates. Look at the fold mountain in this way. If you have two large towels that you have folded, you place them on top of a flat table and you gently push them up towards each other. The folding is going to take place at the area where they both meet. And that folding is exactly what would have happened when you have two plates that are colliding with each other. Folding is going to take place, and that is how you would end up with your mountains. Okay? Um, Major faults. Faults are just the crack in the Earth's surface. So we can have faults. We can have faults at any of the plate boundaries, and then we would have the ocean trenches as well. So for 4, characteristics of intrusive volcanic features. So intrusive means just like the you have to pay attention to prefixes. So you see intrusive, it is suggesting inside. So intrusive volcanic features are those features that have been formed inside the Earth's surface, where the magma has cooled and hardened inside the Earth's surface. So that is how you would end up with your sill, dikes, plugs, batholiths, and laccoliths. The syllabus does not specifically ask you to know about laccoliths based on this. It asks you to know about sills, dikes, plugs, and batholiths. Extrusive volcanic features are the opposite. The fact that it is called extrusive, it means that it happened outside of the Earth's surface. So the lava would have cooled and hardened outside of the Earth's surface to create these features. So we have a caldera, shield volcano, composite volcano, and lava plateau. For the intrusive volcanic features, we have the sill. Sill is formed when the magma lies along the bedding plane. So the sill is going to look almost like a line of latitude. So it is lateral. It's going across the bedding plane. A lot of persons mix up sills and dikes sometimes because the definition for dike is when magma is moving across, when it cuts across bedding planes. But the difference is that for dike, it cuts across the bedding planes, but for sills, it moves along the bedding plane. So for sill, it is going in the same direction as the bedding plane. For dike, it is cutting across the bedding plane. So it's moving from one bedding plane to the next, one bedding plane to the next. That is the difference between the sills and the dikes. So the dike is like sill is like a line of latitude, and the dike is like an angle, probably a 45-degree angle or something that is vertical. Okay? Um, Batholiths now. The batholiths are large. It is much larger than the other intrusive features, and it's the cooling of like a giant magma reservoir. So it cools and hardens, and that is where you'd get your granite from. If you have any questions about those features, you can let me know. Extrusive volcanic features now, the caldera. Caldera really happens when you have a volcano that has acidic lava. It's very explosive, and because of its explosivity, it gets to a point where the volcanic eruption occurs, and it is so explosive that it blows off the whole top of the volcano. After all of the top is blown off, then a huge crater is left inside. It basically leaves a hollow inside of the volcano, and eventually, because it is still a volcano, there is still a crack in the Earth's surface at that point. Lava can still come to the surface. So, inside that crater, you may have smaller volcanic cones being formed. With that as well, there are times when inside the craters would fill up with water. So the water that is captured inside the crater would give us a new feature, which is called the crater lake. The shield volcano, that one is made up of basic lava. So basic lava is runny. It is basically gentle. It's not as explosive. So because it is not as explosive and because it is runny, it would come to the Earth's surface and it flows gently. It flows gently, so it runs over a wider area. The fact that it runs over a wider area, it means that when it cools, the volcano that is going to be created is going to have a wide or a very broad base. That's what the shield volcano would look like, and it is all as a result of the type of magma that is present. So you would end up with a volcano that has gently sloping sides, and it is very, very broad at the base. The composite cone now, just like the word suggests, composite, it is made up of more than one thing. It is composed of alternate layers of lava and ash. Um, the ash would come from the explosive side of the eruption, and the lava would be as a result of the gentle side of the eruption. So it's made up of those two things all in one. Um, the composite cone, because it is made up of those two things, it does not have a gentle slope, just like the shield volcano would have. It would look a little more rugged. It would look like a more like a rugged mountain than what the shield volcano would look like. That would look like a gentle sloping hill that you can probably walk up on. Next one is the rock cycle. I'm going to let you look at volcano for a second. Just a moment. Let me know if you are seeing the diagram of the volcano. All right, good. So it's taking a little while. All right, so intrusive and extrusive volcanic features. That is what we just explained a little. Not all magma that moves through the Earth's crust reaches the surface. Some cooled and solidifies in lines of weaknesses such as bedding planes, faults, and joints. Those features are called intrusive volcanic features. So once it cools inside the Earth's surface, it is intrusive. Whenever magma escapes, it is called lava. Once it cools outside of the Earth's surface, it is called extrusive volcanic features. We have here a diagram that would just show you what it looks like. So we have the batholith, just like we said, it is a large reservoir where it cools and hardens. This would have been our volcano where the magma is actually escaping. You can see the difference between batholith and laccolith. For the laccolith, it is closer to the Earth's surface, and for the laccolith, it actually pushes up the bedding plane. So you will actually see a bulge from it. Whereas for the batholith, you would not see a bulge in the bedding plane from it any at all. This is our sill here, which goes across along the bedding plane, and the dike would go across the bedding plane here. Okay, if you have any questions, you can let me know. This is just a PowerPoint that we would have used in class. So here is a better view of the two types of lava. So it will help you to picture it in your brain, the differences between the two. So we have acidic lava, also called andesitic, or basic lava, also called basaltic lava. Acidic lava is viscous, it is thick and it is sticky, and it is rich in silica. Because of this one, it is explosive and very violent. Um, the fact that it solidifies on contact with air, it means that it will not run very far. So once it comes out of the Earth's crust, it is not going to run very far before it cools. That is why these volcanoes that have the acidic lava, they will not have gentle sloping sides. The sides will be very, very steep because once the magma comes up, once the lava comes up, it is going to cool. So you would have rugged side and it would be very steep. For the basic lava now, it is non-viscous, so it is very runny. So it will just run off the land, so it would flow out like a sheet. Low silica content, it is a lot less violent. It may not even be violent any at all. You can actually watch it running. Um, it flows a long way before solidifying. That is why those volcanoes would have those gentle sloping sides that it would look like something that you can walk up, like the one that we have used for the diagram here. So that would have been your gentle sloping sides. This is an example of a composite cone. So you are seeing the different layers, one of ash and one of lava, and you are able to see lava flow, the crater itself, as well as a dike. This is one of a shield volcano here. It's a little blurry, but you can get the idea of how wide it stretches across for the shield volcano here. And then you are seeing a lava plateau. So the lava comes up on the surface. it just stretches across. In some textbooks, it calls it a lava flow. It just stretches across and it hardens and it happens again. So it starts elevating it. The area just gets a lot higher. Caldera. So this would have been our caldera. This would have been our volcanic cone in general. Then with the very explosive eruption, this area at the top here would have blown off. When the area at the top blows off, some of the materials would fall inside here, but you still have this magma reservoir at the bottom. So there is the potential for magma to still escape onto the Earth's surface. For all those areas that it is going to escape, you would have small volcanic cones formed inside the crater itself. If you had water settling in here as a result of rain or ice melting, etc., that would have been a crater lake that would have been formed. The syllabus does not necessarily ask you to look at ash and cinder cone. That is why it's important for you to use your syllabus as well. You will not be using this past paper because you're doing paper 1, which is great for you. So this would have been, if you're doing paper 2, questions like these: account for the nature of the eruption with the aid of a diagram, explain the formation of a caldera. So you would explain how the caldera is formed and you would use your diagram to assist you in your explanation. And then you are accounting for the nature of the eruption. So you're accounting for the type of eruption that would take place. So you would talk about the type of lava that is present. And then you account for the shape of the volcanoes. So you would tie in the type of lava, the type of eruption that occurs, and then you tie that into the shape of the volcano, exactly how we just discussed a minute ago. Okay. That's it for the volcano section. Let's just look back at the syllabus here. For the rock cycle, formation of igneous, sedimentary, and metamorphic rocks. So igneous rock. Igneous is from the Greek word ignis. Ignis means fire. So that alone can assist you in knowing how the rock is formed. The rocks are classified based on their formation. So that is what is used to classify the rocks. That's how we ended up with the 3 types of rocks in the first place, which is based on how they are formed. So one is formed by fire, one is formed by the compilation or compaction of sediments, and another one is formed from change. So igneous is from ignis. Ignis means fire. That tells you that it is formed as a result of something relating to fire. So the magma, once the magma cools and hardens, that is what would have given you the igneous rock through the process of crystallization. When you have the igneous rock now, it goes through the process of weathering and erosion and all sorts of things happening to it. When the weathering and erosion takes place, you would have small pieces or small parts of the rock that is falling apart as a result of the weathering and the erosion. So you would end up with these small pieces, which are sediments. These sediments would, over time, remember all of this takes hundreds of thousands of years. These sediments over time would settle, usually where water is, close to water. Water aids in the compaction of it. So these sediments would settle on top of each other, and this settling and compaction and building up on top of each other would have created the sedimentary rocks. So the sedimentary rocks, they are basically formed in layers, and it's often near water sources, and you would find things like fossils, the dead animals and plants, etc. Those would assist in the creation of these sediments and the formation of the sedimentary rocks. So that is where the sedimentary rock would come from. Then now you have the metamorphic rock. You're young. I think most of you would probably watch Power Rangers one time or the other. If you have watched Power Rangers, let me know. Just comment which one of the Rangers you are, or which one of them you liked. I liked White Ranger, but that was like a long time ago. But yeah, the point I'm trying to make is metamorphic. You can see a word in there. When the Power Rangers are about to change, they say that it is morphing time. So the morphing is relating to the change that is going to happen. So just the same in this word, the metamorphic rock is suggesting that the rock is changing from one thing to the next. All right, so we have some pink ranger, yellow ranger, two yellow ranger. That's very nice. So nobody didn't like white ranger. All right, blue, red, and green. Cool. So when they say it's morphing time, you know that the change is going to take place. So once you see the morph in your word, it is telling you that this rock was created as a result of changes. These changes would have been as a result of chemical, pressure, and heat. So the igneous rock that you have already, the sedimentary rock that you have already, it would undergo pressure changes or chemical changes or heat changes, and then it would create a new rock type, which would have been the metamorphic rock. So that is how you get from one rock to the next rock to the next rock, and that is basically your cycle. So you have one that is formed by fire. It cools and it hardens. After it cool and harden, weathering and erosion, break it down a little. That breaking it down give you some sediments, little sediments fall off. The sediments, with the assistance of water, they compact together, kind of like cement. They compact together. When they compact together, it gives you the sedimentary rock. Now with those two rocks, they can undergo changes as a result of heat or pressure or chemical. When that happens, that's how you end up with your third rock. So all of what I just explained is how you have your rock cycle. Okay, let me know if you get that. So we can move on to weathering and mass wasting. All right, so the next section is weathering. So the syllabus asks you to define weathering. Um, hold on. Okay, somebody's asking me to go over one more time. I'll just run through it real quick. So, three rock types. The first one, think about the starting of the world or the earth. The first one would be created as a result of magma coming from the earth's surface. Magma cools and it hardens, it creates a rock, which would have been your igneous rock. Remember, igneous from the word fire. It would have created your igneous rock, for example, your granite. Granite or your igneous rock goes through the process of erosion and weathering. So something is wearing it away, whether it is wind or water or whatever. Something is wearing it away. From that wearing away of the rock, you're going to end up with small pieces of rocks falling off, which we call sediments. these small sediments that fall off, they are going to basically group up with each other, and they are going to start compacting on each other. Once you have them all in the same place, water come on it, dry it, water come on it, they start compacting with each other. That process of compaction would have created the sedimentary rocks. These two rocks that we have now, the sedimentary and the igneous rock, anything can happen to them. They can go through any form of changes. So you usually have things relating to pressure, heat, or chemical that would cause them to change. This change is how you end up with your metamorphic rock. So just look for the word morph in it, and you will remember that that is the one that is as a result of changes taking place. Okay? All right, let me know if you're good now. So we're at weathering. So we define weathering. Weathering itself is the breaking down of rocks. There's a cool, very cool song on YouTube. This gentleman, I don't remember his name, but he's wearing a black glasses. This white guy. Um, the song goes something like, "You know about weathering. Break down that rock with weathering," something like that. And then there's a dance for break it down, break it down. So that song can help you to remember exactly what weathering is. It is the breaking down of rocks, full stop, right? Um, the next section that they ask you to look at is the location, process, and the results of chemical weathering. They ask you to look at physical weathering again, and they ask you to look at biological weathering. So, there are three types of weathering: chemical, physical, and biological, or some textbooks call it biotic weathering. So, we may use the terms interchangeably. So, chemical weathering, it means that the rock is being broken down as a result of a chemical process. Physical weathering means that the rock is being broken down as a result of a physical process. So something physical is causing it. And biological weathering or biotic weathering. So the word bio, the prefix bio means life or living. So that one, it is something that is living, whether plants or animal, that is causing that rock to break down. In situ means in place, in its own habitat, at its own area, without being moved. So we have, right, so somebody else is responding in its original place. So we have those three types of weathering. So we can look at, for chemical weathering, they ask you to look at carbonation and hydrolysis. So at one point in the syllabus, it was carbonation and oxidation. This is the last syllabus that CXC had put out. This is the 2015 one. So I figure some of your teachers would have done oxidation. If your teacher did oxidation, you can let me know. There is carbonation and hydrolysis that they're asking you to pay attention to, though. So for hydrolysis, look at the word again, look at the prefix hydro relating to water. So we know that that is as a result of that chemical breakdown is as a result of the substance in the rock combining with water. So for example, feldspar, which is found in granite, it can change to clay when you have the process of hydrolysis taking place. Um, I haven't seen any response relating to oxidation from your teachers, but oxidation is relating to oxygen. that is where you would have the rock would be rusting. You would see that like a orangish film over the rock. That rusting would have been the oxidation. For carbonation now, I'm gonna show you a small PowerPoint on carbonation as well. All right, so never did oxidation. Cool. So it used to be on the syllabus, but it is not there anymore. So I figured that is why your teachers did not touch on it any at all. So we have chemical weathering. For chemical weathering now, just as it suggests, the change is as a result of a chemical process. So it's taken a little while to actually load. So we're not gonna go into oxidation, but we will look at what's the one that we have left? Carbonation. If you are seeing it, you can let me know. All right, so what is chemical weathering and how would you define it? Based on what we just discussed, we pretty much would have been able to answer this question. So I like to inject English language into geography. So once you combine the two words together, what is chemical and what is weathering, then that would assist you in answering the question. So chemical weathering. Chemical means working by means of chemicals, and weathering means breaking down. The action of the weather conditions in altering the color, texture, composition, or form of exposed objects such as rocks. So when you put both of them together, you would end up with chemical weathering is the altering of color, texture, composition, or form of exposed rocks as a result of chemicals from released from weather conditions. I'm just skipping through this because we don't need oxidation. As I said, it's just just PowerPoints that I would have used already. So we are now at carbonation. So carbonation is the process of carbon dioxide dissolving in a liquid. So over here we have a diagram of a rock surface. You can see little shapes here. If you can already identify and name the shapes, you can tell me what they are. I'm hoping someone can tell us what they are. For this, you can do this at your home if you still want to find out, or you can just think about it in your brain. We would normally just run this experiment in class to see exactly how carbonation works. So you take some chalk. Chalk would be representing the limestone, and the limestone is a form of sedimentary rock. And the Pepsi, yes, the Pepsi that you drink, that is literally burning out, that does things to the inside of your body. Let me say that. That Pepsi would act as our carbon dioxide. Just a side note, if you look on the your Pepsi, you will see the level of carbonated beverage that is in there. So that's why we would have used Pepsi for our carbon dioxide, because that's what you're drinking. Anyway, let me stop bashing Pepsi now. So we have chalk for the limestone, Pepsi for the carbon dioxide. And then once you place the limestone inside your Pepsi, you watch it for a couple minutes. Doesn't take very long for the Pepsi to literally destroy the chalk. When it destroys the chalk, you will see that it falls apart, similarly to how carbonation would take place. So the carbon dioxide that is in the Pepsi, it acts on the chalk, the chemical process takes place there. The iron reacts to the oxygen and it forms iron oxide, which weakens the iron. Rainwater, when we look at it in terms of geography now, rainwater contains carbon dioxide, which produces a weak carbonic acid. The acid reacts with rocks. Those are the rocks that are composed of calcium carbonate. So that's especially like the limestone. It causes the limestone to dissolve, and then these dissolving that is taking place, it creates different features in the rocks. So the diagram that we saw first with the little shapes inside the surface of the rocks, those would have been our clints and grikes. It would have been as a result of carbonation where this is happening. So that would have been one form of our weathering that is taking place. This is an example of it being done with sugar cubes, and you would see how it creates a hole in the top. It's the same way that the rainwater would react with limestone. All right. So we can go back to our syllabus. It's taken a little while. For physical weathering, there are two things that the CXC wants you to look at. That's frost action and exfoliation. If you have been with us doing any of the past papers, you will realize that there's a lot of not a lot of exfoliation question, but there is an exfoliation question that keeps repeating. That is just an example of how these questions would be set up for weathering and for mass wasting. So they would basically explain one to you and ask you which one of the process it is. So frost action, just like it suggests, frost means it's from freezing. So that is the continuous freezing and thawing of the rock that that is what would have caused the breaking down of the rock. So it is actually from a physical process that causes the rock to break down. So you have small cracks in the rocks. In the daytime, they the no, in the nighttime, the rocks would fill up with water. Hold on, I'm a little mixed up, just talking from my head here. Um, for the frost action, right? Another name for that is frost shattering or freeze and thaw. So it is the constant freezing and thawing of the rock that would cause it to actually break apart. So in the daytime, rain fills up the rock, or there is moisture inside those little cracks in the rock. And in the nighttime, it freezes. So when it freezes, it expands or it gets larger. If you've ever put a if you've ever put a bottle of water in your freezer and you leave it in there for too long, when you take it back out, you will realize that the bottle swells up, it expands, and the bottle is almost out of shape. It's the same thing that happens with the rock. The water that freezes would have caused the rock to bulge. When it bulges, the rock itself is expanding. The next day, when it becomes warm enough again, the ice melts. So then it keeps expanding, contracting, expanding, contracting. So this constant freeze and thaw will cause the rock to break apart. That would have been the physical process. For the exfoliation now, this is basically removing the outer layers of the rock. Another name for that is, well, some persons call it onion peeling. So this has to do with temperature just the same. So the outer layer of the rock expands and contracts regularly because of the heat in the daytime and the cooling in the nighttime. Heat in the daytime, cooling in the nighttime. When that happens, it causes the outer layers of the rock to start breaking off, almost like you're shelling off an egg. It breaks off, and then that is the process of exfoliation. So again, you see that for this one, it is actually a physical process that is causing the rock to break down. For the biological weathering, or what we call biotic weathering, this is as a result of plants or animals that would cause the rock to break down. Um, Plants can cause the rock to break down by probably growing through their roots probably growing through the rock itself and actually tearing it apart as a result of that. So when you look at it, even though the plant is doing it, it can be looked at as a physical process because something is doing the ripping apart. It is not as a result of the chemical, but it is biotic or biological because it is the plant or the animal that is doing it. So that is one example of how plants can break the rocks apart. Then you have for animals, you may have some animals that actually burrow through the rocks. That causes them to break apart as well. That would have been physical again. Now, from a more chemical, biological standpoint, when you have snails that crawl across the rocks, and I don't know if you've ever seen a snail before, and when you look behind them, you see a trail of that slimy thingy. That thing is actually chemicals from the snail that is being left on the rock that will assist in breaking down the rock chemically. So the chemicals that the snail would put out would react with the rock and cause it to break apart. Earthworms do that as well. So that is the process for biological or biotic weathering. I see Riyadh asking, is that different from acid rain? I don't know which one you're referring to. maybe it's carbonation. If it is carbonation, it is not different from acid rain. It is when it creates the weak carbonic acid as a result of picking up the carbon dioxide. That weak carbonic acid is called acid rain. Definition, cause, and result of mass movement. So there's soil creep and there's landslide. So there are two types that they want you to look at. So soil creep, just like it suggests, is the slow movement. It says creep, so it means that you're going very, very slow. And then slide is naturally faster than a creep. So if you look at it that way, you will know which one is fast, you will know which one is slow. Since you're doing paper one again, the questions that normally come relating to this, they would define one of them for you and they ask you what it is. And then you pick that from your answer. So it's best for you to know exactly what they are. So mass wasting in general can also be called mass movement. It is the downhill movement of materials. So downhill movement of rock debris or soil due to the force of gravity. So it means that you have to have a slope. It can be a gentle slope, it can be a steep slope, but there needs to be a slope because it is moving as a result of gravity. Naturally, if it is a very steep slope, the materials are going to flow faster. So you may end up with a landslide rather than a soil creep. There are factors influencing landslide or soil creep. One of them is water. So the water acts as a lubricant, and for soil creep, it would have made the soil so heavy that it moves a lot more than it usually does. For landslide, it makes it slippery plus heavy so that it actually slides away. So that is where the landsliding part of it would come from. So these would happen in areas where there is wet weather. Um, the more water you have dealing with is the faster the material is going to move and the larger amount of material that is going to be moved. There was I think Myanmar, somebody can check it out right now. Myanmar had a landslide probably yesterday and it was really bad. Really, really bad. There are different types of slow movements. So it's not soil creep alone, but CXC had asked you to look specifically at soil creep. You have rock creep. Any form of creep is a slow movement. Then you have different types of fast movements. CXC asks you to look at landslide only, but you have rock slide, landslide, earth slide, earth flow, rock flow. So the word assists you to determine whether it is fast or it is slow movement. For soil creep, there is usually a diagram that you are asked to there's usually a diagram that you're asked to either draw. If it was paper 2, maybe they would ask you to draw it to assist in your explanation, to show how you can show evidence that soil creep is taking place. Evidence of that is tilting of the poles. Maybe you have that happening in your yard, or tilting of certain trees that you have planted. You'll see that they tilt down the slope. More soil on the back end of a wall rather than on the other end. So you will see that it is basically banking up. You can see that movement is taking place. Riyadh is asking what is rock creep. Rock creep is the slow movement of rocks, just the same way that you would have soil moving. but you're unable to see the movement of the soil because it is a creep. Similar to rock creep, the rock is moving, it's being moved as a result of maybe the water that is below it or just the pressure itself. That movement, once it is so slow that you're unable to see it happening, that would have been your rock creep. Um, for paper 2 as well, you would be required to look at effects of each one of these things. More than so, landslides, effects of landslide. You can just think about that one. Almost for everything that is going to affect something in geography, one effect that you can always write is loss of life, loss of property, or destruction of property, or destruction of farmland, or loss of flora and fauna. All of those things are basically general effects that you can use for anything at all. You can use them for earthquake, you can use them for flooding, you can use it for landslide, volcanic activity, any of those. For those, you can always say that an effect is loss of life, loss of livestock, loss of disruption of services. Those things are general. You can always use those as an example. Number 7, the characteristics of limestone and the processes leading to the formation of limestone features created on the surface. So you have clints and grikes, surface depression, cockpits, swallow holes, and underground features. So we just spoke about carbonation and how carbonation occurs. So after you have the rainfall, taking up the carbon dioxide, mixing and creating that weak carbonic acid, when it falls on rocks such as limestone, it would wear away the limes. Limestone is made up of approximately 50% calcium carbonate. That is why the limestone is so easily eroded by this weak carbonic acid. So the limestone is what will have most of these features forming there. So the clints and the grikes, those are what we saw in the diagram before, where it looks like little gullies. So the grikes would have been the ones that are lower, and the clints would have been the ones that are at the top. So it almost looks like a block. And the part that sinks down would have been your grikes, and the part that is at the top of the block would have been your clints. Surface depression, just like the word suggests, depression means a little sink. It just means that you have a sink in the surface as a result of the acid rain that is falling. Cockpits, in Jamaica, we have the cockpit country. The cockpits are basically just sinks, lots of different sinks, up and down areas. So this area you have a sink, and then the next area you have looks like a little cone. So it's an area of almost all mini mountains. That's pretty much what it looks like. But they are very, very close to each other for the cockpits. And then you have swallow holes, which are large sinkholes. Those are your surface features. Those are the ones that you can see from on top. Those are features of limestone that are formed on top of the Earth's surface. The underground features now, these are the ones that are underneath the Earth's surface. So you have the caves, stalactite, stalagmite, pillars, underground rivers. So we know what caves are. Stalactite, these are the ones that are at the top, the one that has the tight T for top, and the stalagmite, the G in it for ground. That's how I tell my students to remember it. So you know that the one with the T in it is the one that comes from the top. and the one with the G in it, it comes from the bottom. So when both of these are growing down and up, if they meet, they would create a pillar. Somebody's asking if the cockpits would have steep slopes. No, they would not. It is like a, do you know those little buns, um, like the rolls that you serve with dinner rolls? The dinner rolls that are not broken apart yet. So you say you have six or eight or so beside each other, where you have just a gentle raise and then a sink and another raise and a sink and another raise and a sink. So it would look like a bunch of rolls all close together. That's what the cockpits would look like. So pillars is when the stalactite and the stalagmite actually join together. Another word for pillar is column. That's what it would have created. And then you have the underground rivers. That is where the water actually flows underneath the earth's surface. So just an example, you can have limestone in your backyard and there's a cave under there and there is pillar and stalactite and stalagmite under there and water is flowing under there and you don't know about it because it is an underground feature. Yeah, because it is an underground feature. Since we've been doing the past papers though, I have not seen any question at all relating to limestone. I haven't seen not even one question relating to limestone. Since we're already on water, let us just go look at coast instead of vegetation and weather first. So we're going to look at fluvial and coastal processes. Since we're already talking about water, let us talk about the hydrological cycle. The ones that they want you to pay attention to is evaporation, condensation, precipitation, transpiration, runoff, infiltration, through flow, percolation, groundwater flow, and those features. All right. So we know how the cycle works from a let me say a primary school perspective. Just All right, Tyree says he's seen a limestone question before. You can tell us about it, give us an idea. I don't remember seeing one, but you can give us an idea of what the limestone question is like. Um, Evaporation means that the water is leaving the Earth's surface as a result of the sun. When the water leaves the Earth's surface as a result of the sun, um, the higher you go, the cooler it gets. So that water is going to cool. So when it cools, it condenses. And this condensation, once the clouds form clouds, and once the clouds become full, then we would end up with our precipitation. So our precipitation can be in the form of snow, rain, sleet, etc. But in the Caribbean, we would just have our rainfall. Then transpiration is, in essence, similar to evaporation, but it is from plants. So when you have evapotranspiration, it is the water being evaporated from land or water sources plus from plants together. Um, Runoff, just like the word suggests, the water is actually running off the land. I think I have a PowerPoint on it. Let me try to find it. I think I have a PowerPoint on that. I don't know. We can go on without it. All right. So the runoff, the water is actually being carried off the land. In the hydrological cycle, you have inputs, outputs, transfers, and storage. Um, okay, Terry. So that question asked what limestone is made up of. Okay. Yeah, so we said that in our explanation a while ago that limestone is made up of approximately 50% calcium carbonate. So if you do see a question like that, you should remember the calcium carbonate part. Okay? So the hydrological cycle is made up of four different things are happening. There's input, output, transfer, and storage. So the input is what you're putting into the system. So you're looking at it as a system. Input would be from the rainfall. That is what we're putting in. In the Caribbean, we would only have rainfall. Other places, their snow would have also been an input. The outputs now would have been when things are leaving. So that is the transpiration and the evaporation or the evapotranspiration. All right, so somebody saw a limestone question, paper 2001. Oh, that one that we went through. Which one is not a limestone feature? Mm, okay, cool. I don't remember it, but okay. All right, cool. So the output would have been transpiration and evapotranspiration. Then now we have our transfers. So the transfer is when the water is moving from one place to the next. So that is where we get the runoff, the infiltration, the through flow, and the percolation and the groundwater flow from. So these are our movement or our transfers through the system. And then our storage now would have been places that are holding water. So the places that are holding water would have been our groundwater or our aquifers or our springs. So those are the ones that are actually holding the water. So runoff, we spoke about runoff already. Runoff itself is kind of self-explanatory. Another runoff can also be referred to as overland flow. So there were several questions on not several questions, the same question repeating a lot of times relating to deforestation, what happens after deforestation, um, something relating to how deforestation would lead to soil erosion and flooding and overland flow, etc. If you remember that question, you can tell me, but something in relation to that. So that is how the overland flow would come in. So when you remove the trees, remember that the trees assist in the water flowing through and getting to into the surface. The water would have been intercepted by the vegetation, and then you would have the stem flow, and it would flow down the stem, from the stem down the bark, and it would flow onto the roots, and it would actually go under the earth's surface. So that would assist in letting the water infiltrate. But if you have removed the trees, then there is not much infiltration taking place. Nothing is there really to assist the water in going into the soil. Instead, it runs off. So that is what gives you the overland flow or the surface runoff. So you would just have to apply the knowledge from the hydrological cycle towards a question like that that is asking about deforestation and how it would lead to flooding. So then you have well, we said infiltration. There was another question as well that kept repeating relating to, I think it was percolation. It was a diagram that asked, asked you to find, probably name X or something like that. It was right. It was a hydrological cycle diagram. So then you could see the area for evaporation, the area for condensation, etc. And then the area for percolation was labeled X. So you would just have to pay attention to the area where the water is actually going into the earth's surface. So infiltration and percolation is different. Well, generally, water that is flowing through the soil is called through flow once it is flowing through the soil. But when it is flowing through the soil, it is flowing laterally, right? And then infiltration now is the passage of water into the soil. That is just the passing of the water from on the surface to go down into the soil. Then percolation, even though percolation is going down as well, percolation is the downward vertical movement of water within the soil or also within the rock. So it is percolation that would take the water that was just on the surface, take it all the way down to the groundwater storage. So it is percolation that would do that. So that question, we have seen it a lot. So it is something that you need to pay attention to. Groundwater flow now. So we have done evaporation, condensation, precipitation, transpiration, runoff, infiltration, through flow, percolation. So now we're at groundwater flow. So for groundwater flow now, that is the water that is actually moving through the rocks, inside the rocks. So remember that we had through flow, where you had the water that is moving through the soil, that is a lateral direction, so it's going across. And then the groundwater flow is the water that is moving through the rocks and it is in a lateral direction just the same, right? Um, when you have the water passing through, the water doesn't remain at one point. The water flows downslope or underground, downward. When it reaches the groundwater, the upper level of it, the top part of the water, is called the water table. The water that is held inside the rocks, that is what is called the groundwater. So when that water is moving through the rocks, it is called groundwater flow, right? And these rocks generally that hold the groundwater, they are what are called aquifers. So that would take us to here. They are what are called aquifers. And then now the springs. So these same aquifers that we have that is holding the groundwater, there are sometimes small cracks in the surface of these rocks that would allow the water to come through onto the surface. So where that groundwater comes through onto the surface through small cracks, that would have been called a spring. So that is why we said the spring water is clean and blah, blah, blah. That's where the spring water is coming from. And we also did the water table a while ago. If you have any questions about that one, just let me know. All right, so somebody was asking what about groundwater? Kanoha, that's a new name. Hello. Let me know now if you understand. For all the persons who are new and you have not subscribed yet, please ensure that you do so. It makes things a lot easier so that we can actually do this live stream from a cell phone. So we can get to show you some pictures. I can show you the drawings. I can actually draw it and show you, etc. So ensure that you subscribe and ensure that you like the video as well. So Chelsea is asking runoff, through flow, and groundwater all flow laterally. Yes, they all flow laterally. So they run off, like it's as if they're running off the land. Very good. All right, so no other questions. We go to the next one, which is 21, drainage system. So we have been seeing, hi Adil. Ooh, Ramgolam. Nice name. I'm assuming that you're from Trinidad. That's a Trini name. I will try to post it after. Sometimes we have challenges, you know. This is sort of new, but I'll try to post it after. Just ensure that you subscribe. Drainage system, fluvial processes, that is erosion, transportation, and deposition. All right. So for the drainage system, we have seen quite a number of drainage questions. We have seen a lot actually on the past papers. We have seen questions asking us about drainage basin, to identify drainage basin, to identify watershed, um, questions about different parts of the river that we should label. Most of the questions relating to rivers are questions that have a diagram that you are supposed to label something. So drainage system, we explained the drainage basin thing already. We spoke about the pan, the basins that we Caribbean people call it, that we use. So that would have been your catchment area. The actual basin is the catchment area that is in the middle. We have been through that in quite a number of the papers because it's almost as if it is always there. And we posted that a picture of one of those questions on the Instagram page as well. So you can check that out. If you're not following on Instagram, you should go ahead and do so. We post questions daily, so you keep your mind in check. You can post your answers and then we'll like if it is correct. Okay. So drainage basin, that is basically your catchment area or the general area that is drained by the river. The boundary now, the top part of the pan, we referred to it as the top part of the basin, that little edge around the basin, that would have been called your watershed. So that is dividing one watershed from the other. We know that river starts at the source. We've seen a question like that as well. And we know that river ends at the mouth. We know that the smaller river that is going to join a larger river is called a tributary. We know that the point at which the smaller river joins the main river is called the confluence. So those are just terms that you have to ensure that you actually remember. Okay? So for this one, how the syllabus is set up. So you'd have drainage system here relating to rivers. And then under 22, you have the landforms relating to rivers that they want you to pay attention to. And then under 23, they have the drainage patterns that they want you to pay attention to. So we'll go back and forth for these. Then you have coastal system here, what they want you to pay attention to. Then under 22, they have coastal landforms that you should pay attention to, and then they jump into coral reef here. So we will go between 21, 22, and 23. So in relation to the drainage system, we are talking about the river. Where is it that this river comes from? What is the source of the river? The river is usually started at a high point. That comes in handy when you get a diagram where you are required where you are required to tell where the river is flowing from or the direction of flow of the river or something like that. So river is always from up at a high point, and it flows under the influence of gravity, so it would be flowing from high to low. So the starting point, it can be, you need the water to be coming from somewhere. So usually it is a spring that is starting the river, or we can have a upland lake, or you can have melting glacier that's in other countries. So this spring, which is usually the case in the Caribbean, this spring would be the source of our river. So that is where our water is coming from. And then you would have a lot of rainfall, etc., that adds to the volume of water that would have been inside the river in the first place. So the river has three fluvial processes that takes place. There is erosion, transportation, and then there is deposition. They are basically listed according to the stages of the river. Stage one, you would have more erosion taking place. Stage two, you would have more transportation taking place. And stage three, you would have more deposition taking place. So they are basically listed according to what would be happening in each one. The processes, though, they are related, they're specifically linked to the energy that the river has. So I think I've told you already that relating to rivers, you try to, well, I ask my students to link rivers to a person and how they are when they are young, when they are middle age, and then when they are older. So you think of your level of energy as a young person versus the level of energy as a middle aged person, probably your parents, and then think of your level of energy of your grandparents. So that's how we're looking at it. Yourself as a teenager, the second stage, your parents, and then the third stage, probably as your grandparents. So we're looking at their energy levels. I know that some persons will fall outside of the box, and some old people are just really energetic, and you wonder where they get it from. But I'm talking in general, in general. So energy is needed for these processes to take place. The amount of energy that a river has is determined by the amount of water that is in the river, that's the volume of water, as well as the speed at which the water is flowing. So, amount of water, we call that volume. The speed of water, we call that velocity. So, those two things are very important in determining which one of these processes will be taking place. So we have seen a question already where it asks you based on the feature that is formed. I think it was an interlocking spur. It said based on the feature that is formed in the diagram, what type of process, what process is taking place in this section of the river. And then they gave you the option of choosing erosion, transportation, deposition, etc. So that gives you an idea of how the question would have been set up. So rivers are known for erosion. There are basically four types of erosion that we look at. The acronym for you to remember that is CASH, that is CASH. C for corrosion, A for attrition, S for solution, and H for hydraulic action. So once you remember the CASH, then you will be able to remember the four processes of erosion. Okay? So corrosion, another word for corrosion is abrasion. This is the wearing away of the bed and the banks by the river load. So the river load now is what the river is carrying. Think of a load that you are carrying in a bag or something. The river is carrying its own load. So the load can be clay, sand, boulders, pebbles, etc. So that would have been the load that the river is carrying. So for corrosion, The load that the river is carrying, that is what is actually doing the erosion. It's doing the wearing away. So it wears away the bed and the banks of the river. And this is the main type of erosion in most rivers. So in the upper course of the river, you would see a lot of corrosion that is taking place. That's for C. For A now, attrition, this is when pieces of rocks are broken away from the bed, and then because they're broken away, they're usually sharp. So they will hit on the banks, and they will hit on the edges, they will swirl and they hit up inside each other. And that hitting or colliding with each other plus with the sides, it creates smoother edges. If you've ever been to the river before, you would realize that the stones in the river are very, very smooth. They're almost all nice little circles. They're almost so perfect that you want to take them home. This is as a result of attrition, well, all of the erosion processes, but attrition helps the most where this is concerned, because when they break off and they have jagged edges, they collide into each other, which assists them in smoothing down the edges. That is how you would get the smooth circular shape. The next one for S is solution. So solution now is dissolved materials. So some rocks, like the limestone, for example, they would dissolve in the river water. And remember that the limestone may have, as a result of the acid rain, it has the carbon dioxide. So that water now, it causes the rocks inside the river to start dissolving. So that is through the process of solution that would take place. That is for the S. And then we have hydraulic action. Hydraulic action now for the H, that is just the water itself that is actually hitting or acting on the bed and on the banks of the river. So the water itself is causing erosion to take place, just the force of the water. If you have an outside pipe, for example, if you turn on your outside pipe, and you will realize that the earth beneath the pipe, it will wash away rocks and it will wash away dirt and little soil particles, etc., just from the force of the water itself. That is what hydraulic action does. It's just the force of the water that causes the erosion to take place. So that would have been the 4 processes for erosion. Now for transportation, remember that erosion, what was important for erosion was the volume and the speed of the water. For transportation, volume and speed is just as important. When you're transporting things, remember we spoke about the load that the river is carrying. When you're transporting things, you transport them based on the amount of energy that you have. So go back to yourself, your parent, and your grandparent now. The amount of load that you can carry as a teenager would be a lot more than what your parent can carry, or a lot more than what your grandparents can carry. So they would not be carrying so much. They would end up leaving them along the way. But that is for deposition. We'll get to deposition soon. How you carry the load now depends on the amount of water that is inside the river channel. So we have traction, saltation, suspension, and solution again. So let's look at solution first. We just look at solution in erosion, and we said that solution is when materials are, when the chemicals assist in dissolving materials in the water. So since we said that the materials are dissolved, it means then that in terms of transportation, it is that same dissolved material that you're carrying. So the material is dissolved in the water, so you're not seeing it, but it is still being transported. So that is the first one. The second one now is suspension. So when we have the word suspension, we can think of materials being suspended. Suspended materials are lifted up. So they are within the water flow. They're just moving along with the water. Um, if you've ever been to the river before, uh, you may, after you go in the river and you do what you're doing and you swim and whatever, when you go home, you will find very small pebbles or very small pieces of rock, inside your bath suit or inside your whatever the boys wear. So you'll find those little things and you know that you didn't dig up anything, but yet you still find them inside your clothes. So that is as a result of the suspended materials. So they are basically floating around in the water and they are very, very small. So this would be like your silt and your clay sized particles, and they are just carried within the flow of the water. So these you can actually see, but the ones for solution, you cannot see them. So these are the materials that are suspended in the water. So they are floating. Then you have saltation. Saltation now, these are a little bigger. For this one, they bounce along the bed. So they would, it's almost like they're hopping. They hop along the bed from one point to the next, one point to the next, because the river can't lift it up entirely to just bring it along the way. It's either not, they either don't have enough volume of water or it is not flowing fast enough to have these materials suspended just the same. Bear in mind, like we said before, that the transportation of material depends on the volume as well as the velocity of water. So if you have a think about if somebody up the street is washing a car, somebody up the street from you is washing a car, you will have the water that is running down the street. And it will take little stones with it and little soil particles, etc. But if you have a big, like a fire hydrant that has burst off up the street, you would have a larger volume of water that is coming. Not only would you have a larger volume of water, the speed at which the water would be coming would have been a lot heavier. So you would realize that larger materials are being transported as a result of the fire hydrant. Then now, if it is some flooding that is taking place, let us say you have sudden showers of rain and it's a lot of water is coming, it's very, very fast, then you would have a lot more materials being moved and the bigger materials would have been moved. So that's how the transportation works. It depends on the amount of water that you have in the river. It depends on the speed of the water that is inside the river as well. So that takes us to the next one, which is traction. For this one, I like to think of it like a tractor, like a big tractor. So for tractor now, you know that you would only get a tractor when you have a really big things to move. And these things are so heavy that you can't lift them. You would have to roll them. So that is where the traction one comes in. That's the other transportation process for traction. For traction now, it rolls the stone along the bed. This one needs the most energy. So you need to have a lot of water for this to happen. And then you need to have the water to be flowing very fast. You may go to the river again and you realize that you see a very, very large boulder somewhere. And then you probably ask a friend, how that reach there so? Where that come from? But that would have been as a result of the rolling that is taking place when the river had enough energy to actually move it. So for river transportation, just to recap, for traction, these are the largest material and they would have been rolled along the bed. Saltation, these are a little smaller than the big boulders. These are like sand-sized particles, so they bounce along the bed in a leapfrog motion. Suspension, that's like silt and clay, so they are actually suspended or they are lifted up into the water. They are flowing with the water. And then you have solution, where some minerals dissolve in the water, and this one needs the least energy because you won't see it any at all. So solution is always taking place. Okay, let me know if you get the process of transportation, and let me know if you get the process of erosion. Just leave a comment so we can move on to deposition. For deposition now, deposition takes place when a river does not have enough energy to carry its load anymore. So all of that load that you were carrying all along, you're now old, you're at that grandparent stage. So you start putting down the load. Okay? So it means, think about yourself, your parent, and your grandparent again. It means the older you get, the less things you're going to carry. So that is suggesting that in the youthful stage, when you're doing the erosion and all of that, a lot of material is going to be moved. Then when you get to the middle course or the middle stage, or your parents, which we're using to refer it to as, you can still carry some material, but you may not be carrying the very, very large material anymore. You may not be carrying the very, very big ones anymore. So you keep leaving things along the way. That is the deposition. You deposit things when you don't have enough speed, you don't have enough energy anymore in order to carry the load with you. So this can happen when the river is not so steep anymore, or the channel is very, very wide now. So you have a wider area to cover. So the water basically spread out. So it can't move a lot of things anymore. It's not so deep anymore either. Or you just don't have enough energy. Or the river enters a larger body of water. So it would end, so all of the material would have been deposited. So in terms of deposition, because you're doing it based on speed and volume, the larger materials will get deposited first. So the first thing that would be deposited would have been those big stones that we had that were rolling. Those things would have been deposited first. So you deposit them based on their size. So you deposit the big pebbles first, big boulders first, then the ones that were going through saltation, then you would deposit those, then you would deposit the ones that are suspended, and then the ones that are soluble, the ones that have dissolved in the water, they would just go all the way. Okay? So that is it for deposition. So we did erosion, transportation, and deposition for the drainage system. For coastal system, we're not doing them together. We're going to separate them. But just to say, for coastal system, it is the same thing for erosion, same cache processes that are used. For deposition, it's a little different. For transportation, it is similar for transportation, but how materials move along the coast would have been through longshore drift. but we'll get to that one. So landforms, we have river valleys, waterfalls, meanders, braided channels, oxbow lakes, levees, floodplains, and deltas. So I'd given my grade 10, my current grade 10, an assignment, and they were supposed to create a PowerPoint for the processes. So I'm going to try and find that for you. All right, I got it. Let me know if you can see that. All right, so this was like a group assignment, and the students were just supposed to put it together, information on the different features. It's taken a little while. All right, so the first one that it started out with is meander. And then the diagram actually shows us how the meander would turn into an oxbow lake here. So the meander is basically just the curve or the bend that is inside the channel. And these curve or bends, the river basically gets lazy from time to time. And as a result, it would seek the easiest channel to flow. So when the river curves here, it is still trying to find the easiest channel to flow. So on the inner bends here, erosion is taking place. Lots of erosion would have been taking place. And on this section here, deposition would have been taking place. So soon enough, the river will continue eroding both sides until they're close enough together. Once there is a storm or a flood or great volume of water, then the river would cut across the channel here. Once it cuts across the channel here, this area where the deposition was continually taking place, more deposition would take place here, and then you would end up with a straight river and the oxbow lake that is left off. Next one is a river cliff. It's just a synopsis of what the features are and what they look like. This is also known as a river cut cliff, outside bank of the water channel, which is continually undergoing erosion. So that one that I showed you a while ago where the erosion is taking place, that bank that is continually undergoing erosion, that would have been your river cliff. Then you have your point bar. So on the outside, you'd have the river cliff, and on the inner part, you'd have the point bar. That's the inner bank of the meandering stream here. This would have been your point bar, but out here would have been your river cliff. So in this section, this is where your deposition would have been taking place, but in this section, you would have erosion taking place. So this is basically showing you what the meander looks like. So you can see the river cliff on this section, and then you see the slip-off slope or the deposition taking place on this section here. And this is what your meander would look like in real life. So these are actual rivers that have the meander. We already know how a meander is formed. If you want me to go through it, you can let me know. But we already know how the meander takes place, so we don't necessarily have to go through that. But if you want me to, you can let me know. And this is how a river cliff is formed as well. Since you're doing paper one, you're not required to delve into the formation of each thing, but the questions that you would get would be generally diagrams that ask you to label different sections. For V-shaped valleys, we saw a question relating to V-shaped valleys. This was, V-shaped valleys and interlocking spurs together. We saw a diagram and we were asked to identify what feature was formed in that area. There was another question relating to the type of erosion that is taking place in the upper course of the river. So though, since it is a multiple choice exam, those are the questions that you are going to be asked. So in terms of being able to explain every single detail about the formation of each type of feature, you're lucky. This year you will not have to do that. So that's very good. You don't have to delve into those. Since you're just doing the paper one, pay attention to the diagrams, ensure that you know the diagrams, ensure that you are able to label the diagrams, ensure that you know your definitions, as all of these will come in because it is only the paper one that you're doing. So diagrams like these, you have to be able to identify what the things are, but it's very good that no explanation is going to be necessary. So just look at the diagrams so that you are able to see what they can potentially look like, and then it is easier for you to identify them on your exam. We saw a picture like this, and then it asked, what is the name of the feature that is there? They did not have V-shaped valley, but they had interlocking spurs. So you can see the interlocking here that is taking place. So as again, just pay attention to the diagrams so you are able to see where the things are, what they look like, so it is easier for you to be able to identify them and label them on your exam. All right, if you get a diagram like this, and you're probably asked to identify the different areas. So you would have the load here, the riverbed, the river bank, your channel. You have a little meander there, valley side, your V-shaped valley, and as well as your interlocking spurs. We saw, I can't say a couple, but we saw one diagram or one question that was repeated a lot relating to a delta. It asked about, it pointed to one of these, and then it asked for you to identify, for you to name the feature that is there. A lot of persons, I think I posted it on the Instagram page as well. A lot of persons said tributary, confluence, etc. And they were not familiar with what a distributary was. So this area here, this is a delta. So this would have been right at the mouth of your river, where your river is actually depositing into a larger water body. There was another question relating to braiding here, where it asked, I think it defined it, and you were asked to tell what is taking place there. And that was braiding as well. That was also on the Instagram page. And these would have been your distributaries, where you have the river separated as a result of deposition that is taking place in between this area. So if you're not on the Instagram page, ensure that you go and follow the page so you can see the questions when we post them. It is usually ones that repeat, so you get a good idea of what to expect on the exam. Again, if you are watching the live and you have not yet subscribed, please do so that it can make things easier for us at the next time that we plan to do one. You'd be helping us out a lot. This is another picture of a delta. It's just showing you what it looks like. So this is where your river is, and then it is entering into a larger water body, and we're seeing the extensions for the delta. There are three different types of delta. That's what that was explaining. This is showing you a fan delta. So it actually shapes like a fan, so that is why it is called a fan delta. Yeah. More deltas. I think we did potholes in one of the live that we did. We were going through an older past paper. No, it was a 2015 past paper that we were going through, and there was a question that we met upon that required us to explain what potholes were and how they were formed. So these are pictures of potholes. You can actually see the holes inside the riverbed, and you can see that they are very circular based on the erosion processes that we spoke about earlier. This would have been the small rocks or small pebbles that would have broken off the sides that fall in, and once they enter into one of these little holes, the swirling around or the motion as a result of the river itself, the water that is rushing, it would cause it to swirl around, and erosion would take place on the pebble itself as well as on the around the sides of the pothole. So it would basically scour out the hole here while it is smoothing out itself. This is a clearer diagram. This is a nice diagram. Again, we don't have to go into the specific explanations. Since you're only doing paper one, you will not be asked any questions like this. It's just for you to identify different things. So it is a whole lot easier for you. This is showing you how the pothole is actually created. So you have the boulder or the pebble that falls inside. It goes down here, and then you have the circular motion or the grinding motion that is taking place. And that is what creates the deep hole that is inside of the pothole. Again, this was made by my current grade 10 students. They were supposed to do a presentation as a group, so they created this PowerPoint together. You notice that some potholes are large, very, very large, and some are extremely small. Look at this one here. All right, so these are rapids. I have not seen a question on the past papers relating to rapids, but again, it is something that you should pay attention to, because once it has a diagram, the potential is there that they will show you the diagram, and then you will be asked to label something on the diagram or to identify what something is, or you may be asked to identify what stage it would have been found in. So this large boulder here, for example, that is just left in the middle, when you have enough volume of water, again, you can see that the water is fast, but when you have enough volume of water, then it would have been moved. If you have any questions, just let me know. So we go back to our syllabus here. So we would have looked at the landforms, river valleys, waterfalls. I didn't see one on waterfall, but for waterfalls, those are usually at the upper course. They can also be found in the middle course though. They occur when there is a sudden change in the course of the river or a difference in hardness and softness of the rocks. So that is where you would usually find the waterfall. I have seen waterfall questions on the past papers that we have looked at so far as well. The waterfall, I think we went into an explanation about it. The waterfall, it can usually there would have been a horizontal hard rock, and then below that horizontal hard rock, there is a softer rock that is exposed just a little and it erodes quicker. So because the softer rock is eroding, it causes an overhang or almost a little cliff. And this overhang that it causes, the water still flows over this hard rock. So once the water is flowing over the hard rock, it is going to keep, because of gravity, it's going to be a lot faster and it is going to keep eroding or wearing away the soft rock that is underneath. That wearing away of the soft rock that is underneath would create a plunge pool. That area, if you're diving off in a river, you dive off the cliff area, but that area below is like a big pool. It is very, very deep. That is what we're referring to as the plunge pool. Over time, the area would erode even more. So the top part of the waterfall would break off, and then you would still have that overhanging rock, but it would cause the waterfall to basically retreat. So that would have been it for waterfall. We did meanders, we saw the braided rivers, oxbow lakes, we didn't see the levees, floodplains, but we did see the deltas. So for the levees or the floodplain, the floodplain would happen in area of almost flatland, that is flatland on both sides of the river. So you're seeing the river in between, but you have a wide area of flatland on both sides. That area is what is called your floodplain. When when you have a high volume of water in the river channel, it may overflow its banks and then flooding will happen. So that low lying area that is around it, that floodplain is basically the area that would become flooded. For the last one now, for the levees, the material, the when you have the river overflowing its bank, you will have some material that is dropped near to the river on the bank of the river. So the heavier or the coarser material, it is dropped closer to the river. And basically, each time this happens, it builds up on each other. So this natural embankment along the river is called a levee. So we have seen a question like that as well, where you were asked to identify something in the diagram. They asked if it was a floodplain, I think a levee, and I think river terrace. I'm not sure, but something relating to that. If you remember the question, you can let us know. The syllabus does not ask specifically about river terrace, but it has shown up on the exam just the same. The terrace is basically, say you have a floodplain and the volume of water or the river has fallen. It went down somewhere because the channel is eroded a little more, etc. So as a result of that, you would have been left with a high floodplain, and when it went down some more, you have created a new floodplain, or you're creating a new embankment. So those old floodplain that is left perched above the new river channel, that would have been known as your river terrace. So we have seen it pop up already on questions, but again, because it is multiple choice, it is only for you to label. So that would have been it for the landforms relating to rivers. Um, Next thing relating to rivers would have been drainage pattern. There is a video on the channel relating to drainage pattern where we go into detail about dendritic trellis and radial pattern. So you can look at that as well. This one is asking about these patterns and their relationship to the rock type and the geology of the area. That was explained in detail in the video specifically for this objective. So I have not seen a drainage pattern question on the papers yet either. If you have seen one, you can let me know as well. Just type a comment and let me know. But you should know what they look like, because if a drainage pattern question is going to come, it may be where you need to label a diagram or look at a diagram to identify what type of drainage pattern it is. So we're going to go back up and we're going to look at coast. Let me know if we can take a little 10-minute break. I'm not seeing anybody. I'm not hearing anybody. Let me know if you're there. All right, so we're going to take a little 10-minute break and we'll come back to cover coast and coral reef. Are we ready to continue? Let me know if you're ready. All right, so we're going to be looking at coast. We're just starting off with waves. Again, since it's a multiple choice, you can be asked, I can define something and ask you what it is. So your definitions are definitely important, just as important as your diagrams. This is important as well. I have not seen a question relating to it, but you never know. So the distance between two crests, that would have been your wavelength. The measurement from your trough to your crest, to the top of your crest, that would have been your wave height. So it's just giving you wave characteristics here. So the crest is the high point, trough is the low point. Height, vertical distance from crest to trough, and the wavelength is the horizontal distance between crest to crest or trough to trough. Waves are formed as a result of the wind. The wind carries the water until it reaches its maximum. That is how you would get your waves. There are two types of waves. There's constructive and there is destructive waves. Characteristics of each constructive wave, just like the word suggests, it is helping to construct the beach. There's a strong swash and there is a weak backwash. Relatively flat and occur where beaches are gently sloping. They have a long wavelength, small wave height, and the crests are over 20 meters apart. And this is usually operating in calm weather. So they are less powerful than the destructive waves. And if you look at them, this is the type of wave that you would actually want to walk in the water when you see this kind of wave. Now for the destructive wave, I certainly would not want to walk in the water when I'm seeing this type of wave because it looks like it would kill me. So high wave in proportion to the length. There's a tall breaker, so this is where the wave breaks. There is a weak swash, and then there is a strong backwash going down. So the destructive waves, just like the word suggests again, it is actually destroying the beach. So it is taking the material with it. So you see how small this arrow is? It's not bringing a lot of material to leave it. It is taking a lot of material with it. So that is what the strong backwash is referring to. All right, differentiating between the two. We basically just did that, but you can look at it. The main process relating to constructive wave would have been deposition, and the main process relating to destructive wave would have been erosion. The beach gradient for constructive wave is flat, and the beach gradient for destructive wave is steep. This is what both of them look like. So you can see for the destructive wave where it actually takes out the material and removes it and take it back into the ocean. Whereas the constructive wave, it just takes it up and it leaves it on the shore. Yes, pipe water. um, if you, well, the good thing about this exam is that you won't be writing anything, you won't be explaining anything, you will be just shading. So you won't be able to say that waves are formed as a result of the breeze. Okay? Um, these are the coastal processes. So we looked at them already relating to rivers, but this is how they would act on a cliff face since we're doing coast. So we have abrasion here where the rock is being thrown at the cliff, and this assists in the cracking and the erosion of the cliff face. We have attrition here, where this is scouring out the base of the cliff. That is how your wave platform would have been formed. Solution now, this would be the particles that are, well, the chemicals that are acting on the cliff in the water. That's the solution. And then you have the hydraulic action or the hydraulic pressure, where it is the shear force of the water that is actually acting on the cliff face. So these are our 4 coastal processes. Factors affecting coastal erosion: the type of rock, the type of wave, rock structure, as well as the shape of the coastline. If you don't understand that part, you can just let me know and I'll come back to it. I'm not expecting to see this on the exam, on the paper one. But so if you don't understand this section, you can just let me know. These are the factors affecting coastal erosion. Coastal transportation. Transportation, movement of the materials in the sea and along the coast. So movement along the coast is called the longshore drift. Movement in the sea, remember we did transportation already for rivers. So the transportation for rivers would have been the same transportation for coast in the sea. But along the coast, it is called longshore drift. So what is longshore drift? That is the movement of materials along the shore by the wave action. This is usually in a, it takes the form of a zigzag pattern. This is what the zigzag pattern looks like. The zigzag pattern is as a result of the wind direction. So somebody's saying, I don't get it. If I'm gonna come back to it, all right. So coastal erosion. There are some things that will make a coast erode faster, one coast erode faster than the other. So that these are the 4 things here. So the type of rock can make a coast erode faster than the other type. So we have hard rock and we have soft rock. The harder rocks will take a longer time to erode, whereas the softer rocks will take a shorter time to erode. So that is one factor that is affecting coastal erosion. So if, for example, your rock at the coastline is clay or shale, then those rocks will erode a lot faster and you will have your features forming faster. Whereas if your rocks are more resistant, then it will take a longer time for it to erode. In terms of the type of wave, remember we're talking about the factors affecting coastal erosion. So based on the 2 types of waves that we just discussed, the constructive and the destructive, if that area that we're looking at has mostly destructive waves, then that would have been a factor that caused that area to be eroded faster than other areas. Whereas if we have an area that has mostly constructive waves, erosion would not be so high in that area. The other one is the shape of the coastline. So if you have areas that have a headland, because the headland is out at sea, it will be basically attacked first and attacked by most of the waves. So all of the waves would come and hit on the headland. Whereas if it is a sheltered bay, the bay, because you have the erosion on the out in the ocean, the bay is sheltered, so the wave would basically break before it gets into the bay, so that area would not be eroded as fast as the headlands per se, right? So that's another factor that would affect the rate of erosion for coastal areas. And the final one is for rock structure. So depending on how the rock is set up, the structure of the rock. So if you have hard rock, then soft rock, then hard rock, then it would be protected longer because the hard rock is at the front. On the contrary, if you have soft rock at the front, then hard rock, it means that all of the front or the face of the cliff would have been eroded because the rock is soft. So those are the things that would affect how fast an area is eroded along the coastline. So that's what it means when we say factors affecting coastal erosion. So if you understand it, just let me know. If you don't understand it, let me know as well. All right. So we are at longshore drift. We were looking how longshore drift works. So this is the pattern that it would create. It is normally like a 90-degree angle. And the wind direction is extremely important when we're talking about longshore drift, because longshore drift takes it mimics the shape, it mimics the direction of the wind. So if we pay attention to where the wind is blowing from here, when the wind comes in this direction, you will notice that all of the arrows going up, let's picture materials going up on the coast, all of the arrows going up here, they are all in the same direction as the wind direction. And after the materials are pushed up, then they come back down, but not in the same direction that they came up in. So that is how you get that 90-degree angle, up, down, up, down. So as a result of that, because of the direction of the wind, that is why the materials are constantly being able to move along the coast. All right, good. So I see that Destiny and okay, you guys are good. Great. All right. So this is what the process of longshore drift would actually look like. So materials move up the beach along an angle. So based on this, we can say that, all right, the wind direction is coming from here. So because the wind direction is coming from here, remember that it is the wind that carries the wave. So it would it would come in the direction that the wind is blowing. So the material comes up here, it's pushed back down, but the wind pushes it back up, push back down, and it continues and it moves all the way down along the coastline. Okay? Movement of material inside the ocean now. We still have our same processes from rivers. That's attraction, saltation, suspension, and solution. So if there are large materials, they'll be rolled along the floor. Smaller materials, smaller than the large ones, they will bounce, and some materials will be suspended while others will just be dissolved in the water. So that is similar to the river processes. Deposition now is when the eroded material is dropped by the constructive waves. So it happens when the wave has less energy. So there's a lot of similarities between coast and rivers. And the deposition would create a lot of landforms. Similarly, the destructive waves would also create a lot of landforms as well. These are the features of coastal erosion: blowhole, headland, stacks, stumps, arcs, caves, bays, and beaches. All right, so this is a diagram that is showing us all of them together. We've seen questions like this where you are asked to label these things. We've seen questions where you're asked to label this, where you're asked to label this, where you're asked to label, well, every one of them. I've seen a question where you're asked to label every single one. So you need to know this one. So this is how it works. So you have line of weaknesses inside the cliff face. From these line of weaknesses, those same processes of erosion that we just looked at a while ago, those processes of erosion would have been acting on the cliff face and eroding it at different areas. This erosion at different areas will start causing features to be formed. So let us say we start off with this line of weakness here first. Now with this line of weakness right here, we have the wave that is throwing stones at it and it is scouring out that area, and the water is just pushing on it and it is forcing it to open up. So the next thing that we would end up with would be a cave as a result of this area eroding out. So say we end up with a cave right here. Well, now that we have our cave, the water is able to enter the cave. So the water enters the cave and it hits up on the roof of the cave. So some amount of lateral erosion is taking place and it is beating on the back part of the cave just the same. Similarly, because of this headland that we have, remember the headland is jutting out into the sea. So on the other side of the cliff, the same thing is happening. So we have another cave around the other side that is constantly being beaten upon by the water. Then eventually those two caves are going to open out into each other. They're going to meet from the erosion going from one end to the next. They're going to meet. That is how you would have ended up with your arc. So this section here, that is your arc, once you are able to see through the cliff face, that area becomes your arc. Okay? So where the arc is now, with the constant erosion through this area and the weight that is being placed above it, this area is eventually going to crack. So you may have little cracks forming this way going up, and over time, with the crack and the weight that is being placed on the top here, this section will fall inside the water. So when this section falls inside the water, you would end up with a large, tall piece of rock here, which is called a stack. You can remember stack. Well, when you're stacking things, it means that you're putting it up high. So that's how I remember stack. And now that we have this stack standing out in the water all alone, think about it. It is going to be constantly attacked by the water. And this attack is going to be closer to this section here, wherever the water is hitting on. So wherever the water is hitting on here, eventually it is going to erode it and it is going to fall over. It's going to topple over. So now you would end up with a stump. Okay? So that's how we would get stump, stack, arc. We would have had the headland already and we would have the cave and the lines of weakness. Now the blowhole, usually it is formed above the cave. So you have the cave here, you have lateral erosion, the water is coming in, the water is hitting up on the roof of the cave, etc. It keeps eroding, you have little cracks inside, then you end up with a small hole that is at the top. What could also assist in eroding the top would have been, it can be chemical weathering process, or it can be physical weathering process. But weathering usually acts on the top, and then the erosion is acting on the bottom. So eventually you end up with an opening, both of them meet, and that's how you get your blowhole. If you understand this diagram, let me know, because it comes, we see it a lot where you are required to label one thing or the other, but it is usually there for you for some amount of labeling to take place. And we can see that this area here is where our original headland was.